Hi, this is Scott Wilkinson, host of Home Theater Geeks. In episode 319, I chat with Jean Boileau, Vice President of Innovation and Research at Technicolor, about archiving movies using synthetic DNA as the storage medium. So stay tuned.
Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Home Theater Geeks is provided by CacheFly at CACHEFLY.com.
This is Home Theater Geeks with Scott Wilkinson, recorded September 1st, 2016. Episode 319, Archiving Movies Using DNA. This episode of Home Theater Geeks is brought to you by Optical Cables by Corning. Corning's incredibly durable Thunderbolt and USB 3-point optical cables are longer, thinner, lighter, and stronger. Go to opticalcablesbycorning.com to learn more. And by Epson's new EcoTank printers. With Epson's line of SuperTank all-in-one printers, you can print thousands of documents without running out of ink. EcoTank is loaded and ready to print when you are. Visit epson.com/ecotank to find out more. Hey there, Scott Wilkinson here, the Home Theater Geek and editor of avsforum.com. This week's guest geek is Jean Boileau. He is the VP of Research and Innovation at Technicolor. Jean, welcome to the show.
Thank you. Welcome, Scott. Welcome to you, too.
Thank you. Thank you. So glad that you could be here because the topic today is really a mind blower, let me tell you. Before we get to it, I want to make sure everybody knows, those who are watching live at live.twit.tv can join the chat room there, or you can go to irc.twit.tv and you can post questions for John as I go, and I will pass along as many as I can. It always helps if you put my screen name in your message, because then it shows up in a different color on my screen and I can see it easier. My screen name is my name, Scott Wilkinson, no dots, dashes, or spaces. And that will show up on my screen, and I'll be able to pass along your questions. Now, Jean, you've been working on a project at Technicolor regarding the archiving of movies. And this is an important thing to do because a lot of movies simply disappear after some period of time, right?
That's correct. In fact, there's a statistic that I became aware of recently that says that half of the movies that were shot before 1951 have disappeared.
Disappeared? How can that be?
Well, I mean, they don't vanish, although almost, in the sense that these movies were shot on celluloid film, these big reels of films that you see in old movies. And the lifetime of those reels is about 50 to 100 years, which means that after 50 to 100 years, the celluloid support kind of starts to disintegrate or become brittle or becomes like goo. And what that means is that the movie support then becomes such that you cannot show the movie anymore. And in fact, if it degrades too much, you cannot even restore the movie anymore. So the movie is basically gone.
Well, what about the process of digitization, which has been going on for a long time now? You can scan a film with a film scanner and that becomes digital information then, and you can store it on a hard drive or some other medium, but that has its own problems, doesn't it?
Right. So actually, even before talking about that, I should say that the studios really like the celluloid film support. First, because the support has a great advantage, which is that you can eyeball the content, right? I mean, once something is on celluloid, you shine a light through it and you get the content back. There's no notion of format, of different things that you might
decoding,
need to know.
That sort of thing. Yeah.
Coding, exactly. Right. The decoding is done by eyeballing what is there. On the, right. It sounds kind of silly, but it is actually an important point.
Your eye and brain become the decoder.
Exactly. Totally.
Yeah.
And so you're right. But that said, the discs, so both optical and magnetic discs, have become the typical means for archiving movie. In fact, everybody in your audience, I suspect, has movies or music or whatever kind of media stored on the cloud or at home and so on, and it's stored either on optical discs, like DVDs or Blu-rays, or on magnetic discs, so either on their home disk or on the cloud somewhere. Mm-hmm. Now, like you said, both of these types of support have their own problems. I mentioned that the lifetime of the celluloid film is about 50 to 100 years. Optical and magnetic discs, so rotating discs, typically are rated for 5 to 10, 20 years max. So which means that an optical disc, for example, will start to have cracks or will have imperfections on the support. And after a while, you will need to copy the content that is on a disc on another type of support. Otherwise, you're at risk of losing the content again.
Well, this is rather disturbing, isn't it? Because, for example, CDs, which are optical discs, came out in the early 80s. And so that's, like 30 plus years ago. So the earliest CDs might very well be starting to degrade now.
They will be. They will be. And it turns out that many people actually don't keep the CDs or the DVDs or the discs for that long. They're either given to somebody who doesn't return them back, or they're copied,
I understand.
Or basically, the tastes evolve, and a movie you enjoyed 20 or 30 years ago is not really relevant to you anymore, and so on. So it turns out that I would say the typical experience for a normal user right now does not involve a large number of discs that are reaching their end of life. But you're absolutely right. These discs have a limited lifetime. And in fact, I'm thinking not so much for your audience in particular, for example, not so much the discs that include movies, but the discs that people use to store or archive their pictures, right? I mean, oftentimes I've used a lot of CDs or DVDs as medium to store my pictures and home movies and so on. And you have to keep in mind that the lifetime of that type of support is limited as well. So you should plan every so often to actually take your old content and put it on fresh medium.
Yes, and that brings up another problem, which is that storage media or formats change over time. I've heard you give a great example of, if I gave you a floppy disk of data on it, would you be able to read it? Probably not.
Most likely not. Well, so it depends on the subset of the population. Again, your audience might be a little bit different from the general population in the sense that some of them might have old floppy disk readers.
Well, we are geeks after all.
Exactly, but there are few of those, and you need the appropriate operating system and so on to be able to read this. Mm-hmm. So that's it becomes a headache. I mean, yeah, if I give you the latest Star Wars in floppy disk format, so first you would have 500, or actually I don't know, maybe right. 5,000 floppy disks.
Yeah.
So I would come with my truck full of floppy disks to your place. And then, yeah, indeed, the question of how do you read that stuff and display it back on the
yeah, exactly. I'm thinking about my garage where I have a number of zip discs and jazz discs. Anybody remember those? With some old backup data on it, and I still have the drives. Even being a geek, of course, we're all geeks on this bus. But those drives connect to the computer with, say, SCSI. And what computer has a SCSI port anymore? So the means of connection is also evolves and becomes obsolete. So I think you're right. You're exactly right to recommend that if you have pictures, home movies, whatever, on some disk someplace, you really want to keep migrating that to the next format that you think will be around for a while, because otherwise you won't be able to get at those files.
Right, exactly. And in fact, that's one problem that the studios have, for example. Except in their case, the problem is much bigger because they have not just a few movies, they have their entire catalog. So they have thousands of movies that they need to encode very accurately, so using lots of data on a format stored for a while, then migrated to another format as the lifetime of formats expires. So you can see that if you're a movie studio and you have, say, a catalog of thousands or tens of thousands of movies, that would be almost a constant process. It's a little bit like, painting the Golden Gate Bridge, where as soon as you're done painting it,
yes,
you have to start all over again because it took you 3 years to do the painting. Here it takes you, several years to do the migration of the entire catalog, and by the time you're done, you have to start basically all over again with the
next medium,
the next generation of storage medium, right?
Yeah, exactly.
And it's not just studios, but think of any entity that has tons of archival data. I'm thinking Library of Congress. We have this notion that Library of Congress actually stores everything that's floating around, and you can imagine what it's like for them to to manage this huge amount of data at the same time in an environment that technology evolves quite rapidly.
Mm-hmm. And more rapidly. It's in fact accelerating over time. Creamy Corncob in the chat room is saying also CDs and DVDs, even when stored properly in the dark, temperature controlled, humidity controlled, the Mylar still falls off some brands after a while. So what you said before, exactly right. Even if you store things well, it's going to degrade after some period of time.
Exactly. And really coming back to something we just said, for your audience is really do pay attention to your home pictures. I mean, typically people consider their personal picture collection as really one of the key, most valuable items. I mean, typically that's what people go back in their burning house to get out of.
Yes.
And don't think that your CD or DVD or whatever, optical or magnetic disc that you stored it on is going to work for 20 years. I mean, you really, every 10 years, you should be fairly systematic about moving from one type of platform to another.
Yeah. Well, and now we get to the crux of the matter. What you've been working on at Technicolor is something to address this problem in a really amazing way. Tell us the overview of what it is you're working on.
Right. So the idea was, could we come up with a medium that would be able to store movies for a very long time? So the medium itself would be very long lasting, and wouldn't have this issue of technology change that we discussed with the floppy disk example, where in 10 years or 20 years or 100 years, we cannot read it anymore because the technology has changed. So we wanted a support that is very long lasting, that can be read today in 100 years, in 100,000 years. And that led us to looking at the support of DNA. DNA as in the biological DNA that you heard about in your Biology 101 class, which is
D-ribonucleic acid.
Exactly.
The blueprint of what makes every living thing what it is.
Exactly. So DNA is very interesting for a couple of reasons. Number one, it sticks around for a very long time. You might remember stories that that we read about, where every so often we find a frozen mammoth in Siberia in some lake, and the scientists can then read the DNA of that mammoth. And these mammoths are typically 10 to 60,000 years old. So DNA, even after 10,000 years, can be read very easily. So it's a very long-lasting type of support, number one. Number two, it's easy to read DNA in the sense that your body has DNA. Everybody in the audience has a body that has DNA, and there's tons of mechanisms that happens every second where DNA is actually read to produce proteins in your body. So there are enzymes in the body that actually read DNA, and as long as there's life in the form that we understand it and that we see today, there will be ways to read DNA. So reading DNA, unless we all vaporize ourselves to nothingness, I guess, will always be something that will be feasible. So basically, it's future-proof. That's what I'm trying to say, is that it doesn't have that issue of, oh, the technology to read DNA will become obsolete in 10 years. It won't. I mean, unless, again, we go back to a level of technical sophistication that's much less than what it is today, we will be able to read DNA in the future. Our descendants and their descendants and their descendants will be able to read DNA in the future. So if I leave a piece of DNA in a little vial and I put it in a shelf and somehow this DNA encodes some movie information, then people in 100 years and 10,000 years will be able to read that DNA.
I was going to say, yes, we will need to be able to read DNA as long as we are carbon-based life forms. Of course, if we approach the singularity, as Ray Kurzweil has called it, and we all end up being, digital consciousness inside of a computer, that's a whole nother ballgame. But let's not even go there. What I think you're saying, and I think it's very interesting, is even though the technology to read the DNA might change over time, right? You'll get faster computers, you get faster machines, smaller, more portable, whatever. They'll still be doing the same thing, that is reading DNA.
Right.
Yeah.
So really, that was the main, or these were the main two reasons for going for DNA. Number one, very long lasting. Number two, basically a future-proof technology in terms of ability to read what was encoded by us.
And I would say a third point I would add to that might be the data density, which is incredibly high. We have a graphic, number one, that I want to show people here. And so here on the, well, you tell us what we're looking at here, Jean.
Well, so this is a graphic that kind of summarizes what we've been talking about, right? So on the left column, you see the typical media that are used to store or archive content now. So with the celluloid film on top, magnetic discs in the middle, and optical discs at the bottom, and with their current lifetime, and then the DNA helix from biological DNA that, like I mentioned, has a lifetime of a minimum of 10,000 years. So what you're referring to now in terms of density is that if you look at the amount of information that is packed or that is encoded in DNA, and we'll come back to exactly what that means, but
yes.
The amount of information that is encoded in a cube of about a centimeter. So a centimeter is about a little bit less than half an inch. A cube of this would have enough space to encode the content stored on 13 million Blu-rays. So the density is like 10 to 100,000 to 1 million times larger than what you can achieve on tape or optical discs.
Mm-hmm. And we see here 13 million Blu-rays. We also see 625 PB,
petabytes.
Petabytes, yes.
PB.
Which is an incredibly large number.
It's a very large number, and these are kind of actual densities. That is, the theoretical density is much higher, but this is the density that we obtain in practice. So in practice, of course, we don't encode that much content. So it's
sure.
really an extrapolation of the estimated density that we obtain currently, which is about a little bit less than a petabyte per cubic millimeter. So that's about what you end up with a cube that size.
Yeah, this is really astonishing to me because, for example, I've been in the machine room of several studios, Sony, for example, and they have all this hard disk space to store all of their movies and the movie that they're working on and so on and so forth. And they've got a whole room, and it's got maybe a few petabytes of storage in it.
Right.
And that's a whole room worth. And as we said earlier, they're going to have to migrate that to whatever the next storage medium is in some period of time before those disks become unreadable.
Right. Another thing we didn't talk about, actually, as you mentioned, the room, is that typically those rooms are climate controlled too.
Yes, yes.
Whereas DNA storage doesn't need to be in any kind of specific environment. I mean, it's better if it's dark and cold, like everything, but hot and sunny works too.
So this DNA actually sticks around. It doesn't degrade like these other media we've been talking about for tens of thousands of years. As you said, right. the woolly mammoth example. I mean, they've gotten actually viable DNA out of Neanderthal specimens that are 30-some thousand years old. So,
right. So 10,000 years is a pretty conservative estimate, the scientists tell us, yeah, in terms of how reasonable it would be to expect the DNA to stick around without much degradation.
Right. I Am Special asks, Beatmaster, I have to give kudos to Beatmaster. Does this mean there will be movies that actually contain the blood and sweat of the filmmakers? Well, certainly they sweat blood on their making the movie, but that's not what we're talking about here.
Right. So I should say that the DNA we're talking about is not biological DNA. It's not like we take somebody's blood or sweat or a body part of some kind and then somehow twist that or manipulate or do weird or maybe not so weird, but do things to that biological DNA to produce the DNA that encodes a movie. What we do instead is that we create what we call synthetic DNA, basically artificial DNA, from scratch that encodes what we want. And should I describe briefly what that means?
We're going to get to that in a second. I want you to hang on for just a second, because I would like to take this moment to thank one of our sponsors for this episode, which is Optical Cables by Corning. Now, Corning can greatly improve your audio-video workflow with their strong, durable, and far-reaching Thunderbolt and USB 3.0 fiber optic cables. Whether you're into high-end video, photography, audio production, or computing, Optical Cables by Corning will allow you to build a convenient workspace through a superior, long-range connection. Corning's USB 3.0 and Thunderbolt cables are incredibly strong and flexible. They have exceptional cable runs of up to 60 meters, or 200 feet, for Thunderbolt, and 50 meters, or 165 feet, for USB 3, making it so easy to move noisy, space-consuming devices away from your workspace. You can even bend or walk on Corning's cables, and even if they're tangled, it's no problem. They will keep transmitting at top speed. Optical Cables by Corning will help you achieve acoustic and electrical isolation so you can enjoy a clutter-free, peaceful working environment. Among the companies that do exactly that is Universal Audio, which relies on Optical Cables by Corning to achieve acoustic isolation in their studio where they test new equipment, such as their best-selling Thunderbolt audio interfaces. And I can tell you from personal experience and from covering the MI, or musical instrument, pro audio field for a number of years, the Universal Audio is regarded as one of the best companies in the world in these products. So they know what they're doing, and they trust Optical Cables by Corning. Instead of investing in multiple extenders, adapters, and cables, turn to Optical Cables by Corning to establish the connection you need with one simple long-length cable. Optical Cables by Corning are available at all major electronics and professional AV retailers, including Apple stores, Amazon, B&H, and more. Optical Cables by Corning are longer, thinner, lighter, and stronger. Go to opticalcablesbycorning.com to learn more. And we thank Corning very much for their support of Home Theater Geeks. Okay, before we get to synthetic DNA, which is really amazing, we have a couple questions here. I Am Special says, all this is okay until somebody corrupts it. So we have to talk, and another person asked about error correction, which is exactly, Alex C., thank you very much. We are going to be talking exactly about that. So hang on to your hats, folks. So let us talk about the process a little more deeply, because you've been working with, I believe, Harvard University on this project, right?
Right, correct. With a team at Harvard Medical School.
Medical school. So we need molecular biologists and medical people to interface with to really get this thing going, right?
Exactly. That's I mean, basically a combination of bio and computer science really to make it work.
Yeah, yeah. So let's start with this. Obviously, this is digital data we're storing, right? I mean, you take a film, you scan it on a scanner, it becomes digital data. Blu-ray is digital data, DVD is digital data, streaming is digital data, and that's all zeros and ones. So how can DNA store zeros and ones?
Okay, very good question. So I'll use a little prop here to, I guess, hopefully all of you guys can see that. You remember from your Biology 101 class, the double helix, the DNA double helix that is found in all humans and living things. And you know what the double helix is about really is about these little colored things you see in the middle, right? Like
the rungs of the ladder.
The rungs of the ladder, exactly. And you see that there are 4 types or 4 different colored rungs. There's, in this case, red, green, blue, and yellow. And basically they correspond to what we call 4 nucleotide or 4 bases. So basically DNA is made up of 4 molecules, and they're called A, C, T, and G. And that's it. Well, plus, you know, the black stuff around that helps the molecules stick around. But really, DNA is made up of these 4 molecules, and
in a variety of combinations.
Exactly. So what happens is that, you know, the DNA in your body corresponds to a certain sequence of these molecules that is different from the DNA in my body, which is different from the sequence that you find in the DNA of somebody else's body. And basically, everybody has a different sequence of DNAs. And the order in which these molecules appear in your body or my body basically encode the information which is unique about you. So encodes your genes, that basically encodes what's found in your chromosomes and so on. Right? So
the color of my eyes, the type of hair I have, and so on.
Right. So basically the way biology encodes information is by having a sequence of these 4 molecules, a unique sequence of each of those 4 molecules for everybody. And so the idea is to say, well, then let's do the same thing for movies. What we'll have is we'll just have a unique sequence of molecules to represent movie number 1, a different sequence to represent movie number 2, and so on. And so the way we do that is, as you mentioned, we start by digitizing movies. So we transform a movie into a sequence of zeros and ones, right? So which means we have an alphabet of 2 symbols, zeros and ones, right? Now, remember, DNA has 4 molecules, so now we have 4 symbols that we could use to encode that movie. And the simplest way would be, for example, to say the 0, we will turn into molecule A or T, and the 1 we could turn into molecule C or G. So if I go back to my little helix here, right, so this could be a 0, this could be a 1, 1, 0, 1, 0, 0, 1, right? So now you can see that this DNA sequence really can be used to represent a digitized piece of content.
Now,
so
is it true? Is it true? Sorry to interrupt, but is it true that for example, A and T always go together and C and G always go together?
So yes and no, in the sense that some molecules go better together. I mean, that's why you see always these, 2 of them going together. But in practice, you can make some of them work well together as well. I mean, it can be a little bit more complicated, but in practice, we can create, an arbitrary sequence of molecules.
Okay.
And now, so what we did, we started from the movie. We digitized the movie, so we turned it into zeros and ones. And I explained, now we can turn that sequence of zeros and ones into a sequence of 4 molecules, A, C, T, or G. So now the movie will be represented by a long sequence of letters. For example, A, A, C, T, G, G, A, C, right? That would be the beginning of the sequence. And then what we will do is that we will not create a helix like a biological DNA, like I said, but what we will do is that we will write our own sequence. We'll put a molecule A, say for example, then attach another molecule A, then attach another molecule T, then a C, then a G, and so on, and basically create a strand of DNA ourselves, and that will be the way we encode the movie. In practice, the strands cannot be too long, so our movie will be made up of a collection of strands, or like a hair, little hair of DNA molecules, and then another hair, and then another hair, and so on, each one of which will be made up of a sequence of DNA molecules.
Mm-hmm. Another interesting thing you and I talked about offline was the fact that storing digital data, including movies, and that's what you're applying it to here, doesn't use DNA that's in this double helix formation. Right. It doesn't really have to be that, does it?
No, in fact, I'll show you another little prop. I don't know if you can see this. Okay. So this is actually, it's called a biochip. I'm trying to have the angle of the light just right.
We have actually a picture of that as well.
Right. Okay, very good. So you can see well, I don't know if you can see, but the active part of the chip, which is on the top, that silvery part, is basically made of a grid of cells. It looks very much like a memory chip.
It does, yeah.
And the machine that writes the DNA looks very much like an inkjet printer. Where the inkjet printer you have at home is connected to 4 bottles of ink of 4 different colors, right? You have black, blue, red, yellow, and...
Well, actually, it's cyan, yellow, and magenta, something like that.
Cyan, yellow, magenta, and black, yeah. And here it's the same thing. Same thing, conceptually the same thing, in the sense that the DNA synthesis machine, or the machine that writes DNA, is connected to 4 bottles: a bottle of molecule A, a bottle of molecule C, a bottle of molecule T, a bottle of molecule G. And then the head of the inkjet printer will come and position itself on top of one of the cells of that biochip. And for example, let's say we want to encode a specific sequence. We'll say, okay, drop a molecule A now. It will drop one. Then drop a molecule T on top of it, then an A, then a C, then a G. So basically, we will kind of grow. Yeah, and that's the machine that does that. And you see the white squares at the top?
Yeah.
Basically, the white squares at the top are the labels that you saw on the biochip in the previous picture.
Mm. So in other words, a bunch of biochips are stuck into various slots in this machine.
Exactly. So basically, you have 8 parallel heads that write. It's like having a printer with 8 heads at the same time. And you see at the bottom left, you see these tubes with the yellow plug into the machine. You see on the bottom left. Yeah.
Yep.
So that's where the liquid, the molecules of the different different types of molecule actually come into the machine to be dropped on top of the biochip, and that's how we grow the DNA strands, or the DNA hair.
Mm-hmm. Now you showed me in your little model there of the double helix how it might actually look. You don't actually know what it exactly looks like, do you?
That's correct. So I mentioned, we drop molecules on top of each other, and we think it looks kind of okay. So it looks kind of a helix that's gone wrong.
We think it looks kind of like that.
Right. Like you said, we're not quite sure what it looks like, but we think it's something. It's not a helix. It's more of a like a chain of molecules. But frankly, this is speculation at this point because we don't know exactly what it looks like. I think it's somewhere between a hair that is something pretty straight, and this kind of twisted thingy that I just showed you.
Mm-hmm.
But it's not a helix, that's for sure. I mean, like I said, we don't deal with biological DNA. We don't try to recreate biological DNA. We just synthesize DNA ourselves from scratch.
So a couple people in the chat room are kind of working around the idea of, the ethics of this, that, oh, my God, DNA, you could build yourself another being or something. But that's not at all what we're talking about here.
Right, exactly. And in fact, that's one of the, there are many reasons why we don't use biological DNA, but that's one of the reasons too, is that you don't want to, basically you don't want to mess with biological DNA to do weird things. And so for us, it's much easier to just start from scratch. And our synthetic DNA has absolutely no life-giving or life-specific properties. I mean, fundamentally, it is a collection of molecules that are attached one after the other, and that happen to be, the 4 molecules that you find in DNA molecules. But it's really not at all like what you would find in a biological DNA construct. Right. Yeah, I mean, that was one of the approaches that we wanted to take. It's true that we could have considered the approach of taking biological DNA and then maybe slicing and dicing it to create the sequence we would want. But actually, this turns out to be a lot more difficult. And frankly, I just don't think it makes sense. I mean, it's just easier to start from scratch. And think of an airplane, right? I mean, if you want to build an airplane, you can either do flappy wings to recreate the biology, or the biology of living things, or you come up with a different abstraction, which is the airfoil and lift created by air going at speed over that. And basically that's what we do. It's easier for us to just start from scratch, create the sequence we want, and really think of it as a different way to encode content with 4 symbols, 4 molecules in this case, compared to the usual 2 zeros and ones that we've been used to for the past 50 or 80 years.
Now, it's interesting because with 4 molecules, at the moment, they're just representing two numbers, 0 and 1. But they could represent more. You could, in fact, have
That's
even
correct.
higher data density if you used each of the 4 molecules, A, C, T, and G, to represent 0, 1, 2, and 3, for example.
Exactly. And that's what we do, in fact. That's what we do. In fact, well, so there are other issues involved in this, but you're right. You can increase the density by a factor of 2, and we get closer to about 1.5 in practice.
Now, one of the interesting things about these biochips, which we saw a picture of a moment ago, and the machine that writes to them, that actually deposits these molecules into these little hair-like structures, you said it was on a grid.
Right.
And so each of these, each element of the grid, each cell of the grid, and by the way, how big is that grid?
This one, I believe, is 68,000 cells on a chip.
Okay, and
which means that.
Go ahead.
Right. So which means that each cell we will grow a hair of about 128 molecules.
Okay. So that's only 128 bits, right?
Right. So it's not that much. That's exactly what you're starting to get to, which is that to encode, to produce a given amount of synthetic DNA takes time, and is not so easy. Or at least the density that we achieve in practice is not very high in terms of. Actually, it's not so much the density, the throughput, because it takes a while to actually print these in the machine. So we are not at the point where we can crank out a movie in a few seconds or milliseconds. I mean, it took about a month and a half for us to produce or to encode a couple of minutes of a movie.
Muchacho is asking, you have to start with something like RNA, if I recall biology. How do you start from scratch? Well, the answer is you have this machine that has these 4 jars of molecules, and it inserts each one in the chain as you go. And that, as you say, that takes some time, right?
Right. And we don't need RNA in this case because we do not deal with biological DNA. He's right, absolutely, in terms of what would be needed if we were using biological DNA. But since we basically create our own assembly of molecules, of DNA molecules ourselves, we don't need to get RNA involved in this process.
Now, so a movie, if you were going to store a movie in this way, it would require many of those strands, each of which is only 128 bits, representing really only a few pixels.
Exactly. And
so how do you know? How do you know which of those strands are which pixels?
Very good point. Very good question, I should say. Actually, before I answer the question, I just wanted to show your audience what a movie looks like. So you see, this is a little vial with water and
like a few drops of water in it.
It has a few drops of water, and this has actually a large number of million of DNA strands floating in it, representing a movie which is called A Trip to the Moon. It's an old movie made by Georges Méliès, who was a French director at the beginning of the 20th century. The reason why we started with that movie, or used it as our proof of concept here, is because it was the first movie with special effects. For example, Technicolor is a big company involved in special effects. It's one of the movies that we restored, or that Technicolor restored a few years back. And it's historically significant for a number of reasons. So we selected that movie. I have to say it's a fairly short movie, which means that we didn't have as much information to encode to produce that movie in DNA. But basically, that's what the movie looks like. And you're right. It's made up of a few drops of liquid with tons of little DNA hair strands that float in it. And then now the question becomes, how do you get this back into something I can see on my screen? Because that doesn't seem like an obvious, completely obvious step. And what we do is that we use machines that are called DNA sequencing machines that basically read long or short sequences of DNA molecules and tell you what those sequences are made of. So it basically spits out the sequence. For example, we would say, oh, that sequence is made up of AACTG and so on. Right? So once we have the sequence of letters, then we can go back to the zeros and one, and from that we display the movie. But
hang on one second. Before you go on, because this is a whole nother area that I want to definitely dive deeply into. How do you get that information back out? And I know that there are a number of people in the chat room who are asking that same question. But before we talk about that, I'd like to thank our other sponsor for this episode, which is Epson. Epson's revolutionary cartridge-free EcoTank line of printers for home and office introduce a new age in printing. The EcoTank ET4550 wireless all-in-one printer doesn't use ink cartridges. Instead, it features an amazing, innovative, refillable ink tank, earning it the title of CES 2016 Innovation Awards honoree. You'll have no more out-of-ink frustration. It includes up to 2 years of ink, equal to about 11,000 black pages or 8,500 color pages. You can save up to 80% on ink with low-cost replacement bottles. It's also powered by Precision Core printing technology. It has auto two-sided printing and a 30-page auto document feeder, and easy wireless printing from tablets and smartphones. All EcoTank printers deliver an unbeatable combination of convenience and value. With Epson's EcoTank line of printers, you'll have the freedom to print without running out of ink. The Epson EcoTank system was named the 2016 Small Biz Windows Printer of the Year. So visit epson.com/ecotank today to transform the way your home, office, or work group prints. For the best combination of ease and value, turn to the Epson EcoTank printers. That's epson.com/ecotank. And we thank Epson very much for their support of Home Theater Geeks. Epson, exceed your vision. Okay, I'm speaking with Jean Boulot, VP of Research and Innovation at Technicolor, and we're talking about a really amazing thing here, storing movies or other digital data. We're talking about movies today since this is Home Theater Geeks after all, using DNA as the storage medium. And we've talked about how this is now, the data is now written into a sequence of molecules that are used in DNA that are called A, C, T, and G. And they sit on a biochip, and they have little hair-like structures coming out of these 68,000 cells. And each one is only about 128 molecules long, 128 bits, which is maybe a few pixels. And so now the question becomes, how the heck do you recover that data?
Right. Right. So you use a different machine, which is called a DNA sequencing machine, which basically will take as input DNA molecules or DNA hair, DNA strands of various lengths, and give you as output the exact sequence of molecules that make up those strands.
Now we have a picture of that machine. Here it is.
This is the machine that we use for our experiments. The machine actually, compared to the Epson printer you saw in the commercial just a few minutes ago, this is about twice as large. I mean, twice as wide and twice as deep, and maybe a little bit less than twice as tall. Right. So that gives you an idea of what this looked like. I should say though that the technology for reading DNA is improving at just amazing rates. You know, if you think that what goes on in electronics goes fast, you have nothing compared to what these bio guys do. I mean, it's incredible. So this was the machine we used last year. The prototype that I saw about a month ago is the size of an iPhone. And what you do is you come with your drop of liquid with DNA stuff in it. You drop the liquid in a little receptacle there. And the reader is actually connected to the USB port of your laptop. And boom, the DNA sequence comes on your screen. So we're not quite there yet at the point where reading DNA would be as simple as plugging a DVD or Blu-ray reader in your USB or other port of your laptop, but we're getting really close to that.
So this is not a real-time thing. This is not, you couldn't take that vial and say, oh, I'm going to watch Trip to the Moon tonight and stick that in a device and watch it directly from the DNA.
You're correct. You're correct. The reading process is still very slow, but I just wanted to illustrate still the amazing difference that happened in a year. I mean, when you go back to 4 to 8 times the size of that printer, with no interface to laptop of any kind, to something which is the size of an iPhone 5, I should say, a smaller one, with direct plug into the USB port, it's quite dramatic, and that happened in less than 18 months.
Unbelievable.
So think about what that means. Another 18 months, another 18 months after that. So that puts yourself about 3 years from now. And 3 years from now, I anticipate that we'll have something again that might not be necessarily real time, but where you decide, okay, tomorrow I want to watch that, then you put your drop, and boom, the movie is available the next day for watching. So I might be a little bit optimistic, but I really think the rate of change, the rate of improvement is just so dramatic that it really opens doors that are pretty amazing. We started this project 3 years ago, and when we started, everybody thought we were lunatics or delusional, or both of the above. And then we actually managed to do the movie and get it back entirely last year. And now we're working on this next generation technology, which will hopefully make it much faster and much cheaper. And so I really think that if things go according to plan, 3 years from now, we'll see the first commercial trials of this.
Wow, 3 years. One thing I wanted you to speak a moment about is the fact that, as I've said earlier, and you described, each of these little strands that are sitting on this biochip have 128 or so bits on them. And so the movie has to be broken up between many, many of these strands. And you said to me offline that each of the strands has a unique identifier that actually allows the sequencer, the reader, to put them back together in the right order. That seems amazing to me.
Well, we have to. Otherwise, how would you put it back, right? I mean, if I give you this vial and I say, all right, I want to read the movie, and there's a million strands there, you need to put the strands back together in the right order in order to get the movie back. And so what we do, exactly like you said, out of the 128 molecules or bits that are available on each strand, we reserve actually about 20 of them to represent an index that basically will indicate which hair we're looking at, right? So if we divide the movie into hair number 1 or strand number 1, strand number 2, strand number 3, up to strand number 1 million, right? So now we have a way to recognize which one is which and then put them in order correctly. What we do also is that we add a few bits to indicate information about the movie. For example, the title, I guess we could put actors and so on. I mean, the problem is that we would like to put more information, but of course, the more information you use, the less useful information you have to actually encode the movie. However, having that metadata in a way, that site information available in the strands allows you to do search and retrieval much faster than you would be able to do without that information. And so it gets a little bit more complicated, but I can illustrate this with a simple example. Suppose this vial here had not just one movie like what I have now, but had an entire catalog of, say, 1 million movies. And out of that 1 million movie, I want to find The Wizard of Oz. So find me, the DNA strands that correspond to the Wizard of Oz. So I have two possibilities at this point. I could either read the entire catalog and then, get the Wizard of Oz, or I could just try to see if there's a way to biologically select only the strands that are relevant to the Wizard of Oz, and that's what we're trying to do. So basically, almost have like a biological search engine where if I search for the Wizard of Oz, I can do it there in that little vial and get the result without having to decode everything from DNA first. Do you see what I'm saying?
Yeah. That makes a lot of sense. It just requires the dedication of a little bit of information to tag each of the strings or strands as, this is for the Wizard of Oz, this one's for Lawrence of Arabia, whatever.
Right, exactly. Right. So we're getting there. We're just starting to look at this kind of mechanisms, but it opens again all kinds of interesting, like a biological search engine. How would that work?
A biological search engine. That's really wild. One thing I really would love you to address for a moment is the error correction. Again, offline, you told me that writing synthetic DNA has a very high error rate. So how do you compensate for that?
Right. So it's really a key problem. I mentioned earlier that the machine to write DNA is a little bit like an inkjet printer connected to 4 bottles of molecule in this case. And what happens is that if you tell the machine, could you drop now a molecule A and then a molecule C, sometimes what happens is that instead of dropping a molecule A, we'll drop 2. There's A and there's an extra drop that falls there that you're not aware of. And sometimes, and then you say drop a molecule C, and what happens is that the tube that comes from C is kind of clogged, and instead there's a little bit of leftover from T, so you get a T instead, or you get nothing, so there's all kinds of issues that can arise really when you write DNA. And you're right, the error rate is quite high. It's close to 1% per molecule. That is, every time you write a molecule, the likelihood that you write the wrong one or that you don't write anything is about 1%. So it doesn't sound very high until you realize that every strand or every hair of DNA that we write is about 128 long, which means that over 128 molecules, the likelihood that you have at least one error is very high, right? So basically, every strand will include an error.
Right. At least one.
So, at least one. I mean, some of them won't. Some of them will have many.
Yeah.
And so what we need to do is be able to protect against those errors. Especially think about, what if the error is on the index number, the number.
Yeah.
Right. Then if we have an error there, then we'll put the hair in the wrong position in the movie, so we won't be able to decode the movie accurately. Right. So there's all kinds of mechanisms we have developed to do basically error correction for DNA. So there's been a lot of work on error correction for just about every medium you can think of. There's error correction on your DVDs, on your Blu-rays, so that when you scratch the Blu-ray with your nail or whatever, it can still be read. There's tons of error correction mechanism on your cell phone, so that the connection to the base station happens accurately, even when you don't have good RF configurations and so on. And similarly here, what we did is that we studied the process of actually writing DNA and came up with mechanisms to compensate for those errors. Sorry, both writing DNA and then reading it back, because there are also some errors when you read. And the really, to me, the key result that we achieved last year with the movie The Trip to the Moon was to show that these error correction mechanisms were effective, in the sense that we could encode the movie in DNA, store it, retrieve it, and then display it back on the monitor with zero error. And that was really an exciting result.
Yeah, no kidding. Okay, we got several questions from the chat room. Let me pass them along. One is from Untoward. Would reading the data destroy it?
Yes, but it's not a problem. It turns out that biology provides some interesting benefits. In particular, if you have DNA strands, you can make millions of copies of it very easily. So that's why when I showed you the vial, I said there's 1 million copies of the movie. What we did is that we produced the first copy, and then we made 1 million copies of that. And that's very easy. There's a process called PCR, polymerase chain reaction. You can look it up. It's a very standard process in biology, where you take a sequence of DNA and you make, basically you make two copies, then 4, then 8, 16, and so on, by doing changes in temperature and so on. There are machines that do that automatically. So what we do is that we make 1 million copies of the content, select some copies of that, and they get destroyed, but that's not a big deal because we can make another 1 million copies very easily.
Got millions of copies, yeah, exactly. In fact, SSB 201 mentions that sequencers rely on amplification and replication of the sample. And he asks, how is that dealt with for synthetic DNA? Well, the same, I guess.
It's exactly the same, yeah. I mean, PCR that I mentioned is exactly the amplification that he's talking about. Yes, that's correct.
Emily the Strange asks, how does this whole DNA process affect sound? The audio of the movie is captured as well. Sure. It's just digital data, so it doesn't affect the sound at all, really. It's just the same zeros and ones that you would find on a Blu-ray or something like that, right?
Exactly. You know, there's nothing magical about DNA. I had some people ask me, does it sound better after you get it back? And I wish, you know, that would be great. Yeah. But it's, you know, what we're really talking about is, think of it really as your DVD. I mean, it's just a medium to store content, except, of course, it's, you know, it's a little bit exotic at this point because we're not used to storing things on DNA. But whatever, I mean, basically you get from it what you put in. I mean, if you encode sound with high quality, you know, tons of bits per sample, high frequency, and so on, then you'll get great sound back. If you encode crappy sound, you'll get crappy sound back. But really, there's nothing that prevents you from even adding text along the movie. In fact, that's what we did. We encoded some script data as well. So you could have a combination of, you know, movie, sound, script, and other things.
User 6918 asked a similar question. With 128 bits, how do you get Blu-ray quality? Full 4K, full HDR, Dolby Atmos, blah, blah, blah. Again, the answer is the same. It's just bits. It's the same bits as you would find on any other medium, just stored in this unusual way.
Exactly. It's exactly what you put in. I mean, you could put 8K, 200 frame per second movie content in there if you want to, or you can put VHS quality. I mean, it's really up to you, frankly.
Yeah.
I mean, in practice, we anticipate that given that this is not a storage or archival medium that is as easy yet to deal with as, you know, magnetic disk and so on, that it's going to be used for high value, high quality content, right? I mean, we anticipate studios will use this for their best movies, the ones they want to have around for a long time, as opposed to some crappy stuff that they want to get rid of.
Yeah, right.
But really, there's nothing that prevents you from using that for really any kind of data storage.
Mm-hmm. I guess it's probably too early to answer Hermes' question. Is the technology proprietary, or will it be open source? Who knows, right? You're in the experimental, prototypical stages right now.
Yeah, I mean, right now it's hard to say. Well, so we're still at the point where we're trying to identify what will be commercially viable. I mentioned earlier that the technology we've used so far is something where it took a month and a half to do a very small amount of movie data. It took 3 biochem PhD students to manipulate to operate the equipment, and it took several tens of thousands of dollars in liquids and equipment and stuff like that to make it work. So you can see that we are far still from the point where this is something you can use for your own home movie, or even that the studios could use yet for even for their best movies. However, as I mentioned, the rate of change is really quite dramatic. But at this point, there's still a lot of uncertainty around what technology will work. And so I would say it's a little bit early to tell, because we don't know exactly what it is that will be, the winning technology, really. Yeah.
Number of questions are related here. I Am Special says, I think the lifespan of the data is the crux of this research. Good Sound says, how robust is this form of storage? Does it need to be refrigerated? And Conky says, why is the longevity of this technology longer than current media? Can't it deteriorate too?
So DNA can deteriorate to some extent with cosmic rays. There are some mutations and so on, but the deterioration is very slow. And keep in mind, again, that we have 1 million copies of something. So let's assume the cosmic rays actually, during storage, modify even 1,000 copies of a strand. There's another 999,000 copies of it floating around. So you just do a majority rule there for the coding, and you end up with the original content. So what I'm saying is that the rate of degradation of the DNA during the storage process is very small compared to the error process during writing and reading. And so the error correction codes we have to protect the reading and writing are more than strong enough to compensate for any error that might occur during storage. So in fact, we don't anticipate any issue with the degradation. And there was an earlier question that, sorry, even over thousands of years.
Yeah, thousands of years. That sound Pro 69 is why it's more future-proof. We talked about this at the beginning of the show, that DNA, you'll always be able to, even in 1,000 years, unless we are no longer DNA-based creatures, you'll always be able to read DNA. So
exactly.
That's why it's future-proof.
And there was a question about, do we need special equipment to store it? And the answer is no. We can leave that on a shelf and come back in 1,000 years, or somebody else comes back in 1,000 years to pick it up, and they'll be able to use it straight off the shelf. In fact, the George Church, the prof at Harvard that we do this with, said, even if the facility burns down, you can still scrape the bottom with your shovel and get the DNA from the dirt. so it is quite robust to accidents.
Mm-hmm. I Am Special asks, why did they choose movies and not written material like, say, books?
So very good point. In fact, the team at Harvard that we started with a book. George Church wrote a book called Regenesis, and he started by trying to encode that book. And in fact, that's the paper they wrote as a result of that is what triggered me to actually get in touch with him and get the project going. The reason why we wanted to look at movies is that book data really takes no space at all. I mean, an entire book is a few hundred kilobytes. The reason why we start with the movies is because Technicolor, of course, is heavily involved in the production of content and movie in particular, and therefore we were interested in looking at the technology that would work for movies. And movies are interesting because they're really orders of magnitude bigger in terms of amount of data than books. And so the challenge that we had, or that I put in front of George when we started the project, was to say, look, I'm interested in continuing this, but there are two directions I'd like to go in. And number one is scale the amount of data we can encode or we can create, number one. And number two is be able to retrieve the data perfectly, because in his experiment, he could not retrieve the data perfectly without 100% accuracy. And in our case, we absolutely needed to be able to come up with error codes that would enable us to read the movie back entirely and not just pieces of it, because then otherwise that would fail as an archival mechanism. And so that's what we did as a focus of the project.
Certainly, since Technicolor is so heavily involved in the movie business, makes sense that you would want to use this technology to store movies.
At least start with that. Yes, exactly.
Yeah. Muchacho asks, if you just need ones and zeros, why not just use two types of molecules?
You could. It turns out that using 4 is better for at least a couple of reasons. You mentioned, Scott, one of them, which is that you can have higher density with 4 symbols compared to 2 symbols. And number 2 is that it turns out that some molecules are better than some others in terms of getting, staying together easily. So, and we could have, say, for example, only A and T, but okay, so that would be a little bit difficult to explain. But there's an issue of modulation that we use to help us with the errors. Basically, having 4 symbols. Think of it as 4 degrees of freedom. You have 4 degrees of freedom compared to 2 degrees of freedom, and there are some things that enables you, especially in the era of error correction. You have basically more freedom to come up with stronger error correcting code with less overhead.
Okay.
Sorry, that's getting a little bit technical, but that's yeah.
Hey, we're all geeks on this bus. That's totally fine with me. Hodor asks, surely pits and lands, that is how data is stored on an optical disc, can be scaled down eventually to the size of atoms. Why is this simple approach inadequate?
So yes and no. It's not so easy to scale it down because think, how do you make these little patterns on the disk, right? I mean, you at some point you have maybe a light mechanism, so you will be limited by the wavelength. And then you hit the same limits that people in semiconductors use. And you're right. I mean, they're going down to smaller and smaller dimensions. But if you notice, Moore's law, in terms of the size of the basic patterns on chips, has not really improved. I mean, we're at 815 nano, and it's not going down. The DNA is interesting because because getting that high density from the get-go is easy, in the sense that these molecules are basically designed or have become such that they get together well. I mean, go back to my little thing here, and you see that these two go well together, these two go well together. So these is a little bit more complicated, but I would say the space filling properties of these molecules together is very high, which means that you have, just by design, so to speak, a super compact way of representing content. You're right. I mean, they eventually. Assuming that we control maybe down, to X-ray lithography and so on, down to smaller pattern size will increase the density of optical or magnetic media. But we are right there already, actually thousands of times more dense with DNA. The other thing is the DNA is a volume type of solution, right? I mean, your disks are disks, and you can have layers, but it's difficult to make it a 3D construct, right? In our case, the constructs are basically 3D. I mean, their hair can be next to each other, very, very densely packed, and that's what gives you this incredibly high density.
Mm-hmm. I just one last thing, because we're running out of time here, but Hodor made an interesting comment here that I just had to bring up, which is, I don't know if you watch Star Trek: The Next Generation.
Some of them. Mm-hmm.
Some of them. There's one episode that you really should see. It's an episode wherein an ancient Forerunner civilization has encoded a video message, a holographic message, as it turns out, and you can retrieve it by combining DNA fragments from several different species.
Oh, okay.
So,
no, I haven't seen that one.
If you haven't seen that one, I'll send you the link to that particular episode. You really should see it, because what you're talking about here is kind of, on the way towards Star Trek, which is really so cool. So
interesting.
Last question from I Am Special. Does Jean envision that they will eventually be able to store every movie ever made?
Yes, of course.
No reason why not, huh?
Actually, let me see if I have here. I'll show you with my little Lego thing. So all the movies made so far, all the movies ever made so far would fit in this.
Oh man!
So now storing all the movies ever made, 10 or 20 years from now, is probably going to be much bigger, because the amount of movie content produced, not just professional but user generated, is very high. But still, this is something that's feasible. The big hurdle to me is going to be the cost of it. For the foreseeable future, this is going to be a technology that will be more expensive than magnetic or optical. So the question then becomes, do you really want to spend the money and the time to encode the video stream that comes out of your security camera at home? Probably not. Do you want to spend the time and money to encode your favorite family memories that are held on film? Maybe. As a studio, there are some movies that you're care to store and archive for the long term, and I'm sure there are some that you don't really care too much about, and so you'll spend less money and care for those. So I think it's going to be a trade-off between ease of archive, cost of archive, versus the value of the content to the person doing the archiving. I mean, so it's always a little bit the same, and I think it will play out the same way in this case, with slightly different trade-offs compared to magnetic and optical.
Sure. But with a much longer lifespan. Hodor reminds us that the Star Trek episode that we want to look at here is called The Chase. I will send that to you in an email, okay, but you should really check it out. Meanwhile, we've run out of time. And as I knew it would not be difficult to fill an hour with this stuff, it's absolutely fascinating. I want to thank you so much for being here. That's Jean Bollot, Vice President of Innovation and Research at Technicolor, talking about archiving movies and other data in DNA. Jean, thank you so much.
Thank you, Scott. It was a pleasure, and hopefully your audience enjoyed it too. And
I think so.
Stay on the lookout for your vial of DNA in your pocket a few years from now.
Yes, well, someone here, Creamy Corncob, wrote, "Mind blown," which was my goal for this show. Now, unfortunately, the Technicolor website, technicolor.com, really doesn't have much information about this, does it?
No, so there's not a whole lot that's available for, I would say, a general audience about these technologies quite yet. Actually, my mistake, Scott, I told you I would send you a couple of pointers, which I haven't done, but I'll do that later today, and you can maybe forward that to, or make it available to your audience.
Sure, happy to do that.
I mean, I wrote like a 2-page article describing basically at a high level what it is that we're doing. And basically that summarizes what we've talked about here. And I can point you to a scientific article that the Harvard guys actually wrote recently, or a couple of years ago. But I have to warn you is that it starts up there and it takes up from there. So,
well, I'll tell you this. I also wrote an article about this work, about your work specifically, on AVS Forum last April, I think. So it'd be pretty easy to search AVS Forum for DNA. It's probably the only title, the only article with a DNA in the title. So that'd be another place to look. Anyway, thank you again so much for being here. And I look forward to following your work in the future.
All right. Thank you for having me.
You bet. You can always find me at avsforum.com. You can email me at scott@twit.tv. And you can follow me on Twitter at htgeekscott and at avsforum. You can always find previous episodes of Home Theater Geeks right here at twit.tv/htg and on our YouTube channel, youtube.com/twit-home-theater-geeks. Next week, my guest geek is scheduled to be James Niehaus, the director of photography on IMAX's A Beautiful Planet, and plenty of other titles as well. So we're going to be talking about videography and shooting in outer space and all kinds of really cool stuff like that. So I do hope you will join us. Until then, geek out.